Okay, what I'd like to do is look at page 364. Okay? And one of the aspects that we deal with talking about gases is the volume of gases are measured in either liters or milliliters. Okay? Pressures. Yes. Okay. Fair enough. Okay. Now we're going to start talking about chemistry. Got it. Okay. So gases measured in liters or milliliters. Okay. The conversion between them is very simple, just like grams and kilograms. If it's in milliliters and you need liters, you would divide by 1,000. If it's in liters and you want it in milliliters, you'd multiply by 1,000. Okay. So pressure. The standard unit for pressure is atmospheres, but sometimes it's given in millimeters of mercury or possibly torsellies, known as torrs, and another one could be the Pascal, if you remember that from physical science, and then ultimately kilopascals, which again would just be 1,000 times larger than that of a Pascal. And then when it comes to temperature, the standard unit for that is degrees Kelvin. So when we're measuring these gases, we begin with that of Boyle's law and Charles's law, and we'll get further into that at a later time. But we want to concentrate on, pressure conversions. Okay. So what that means is on page 364, it gives you on table 1 the unit of pressure. And notice that millimeters of mercury and torrs are the same thing. For the most part in this chapter, we're more so concerned about what you see in the atmosphere area. That when we're converting from atmospheres into millimeters of mercury or torrs or kilopascals, there are certain conversions that we want to go through. What that means then, okay, is something, this is what I was talking about earlier as far as color coordinating some of these organic reactions that what we would see. So I can imagine click, 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 click. So anyway, with that, okay, so how many of you have heard of atmospheres before? I mean, just even that term. Why would you have heard atmospheres in your daily life? Especially when it comes to the news, a certain portion of the news. The weather, right. Because one of the aspects that a meteorologist will be talking about given the forecast is talking about, okay, here's the temperature ranges amongst different parts of the state, and our atmospheric pressure is at this level. Usually for this area, I think it probably revolves around 29 inches to maybe 31, and I'm not quite sure if that's entirely accurate, but I'm just trying to think off the top of my head. I think that's for the most part. When the pressure drops, have you ever heard that your grandparents are saying, oh my, or oh man, or oh my, there's a storm coming because my knees are starting to hurt? Does this sound familiar? Never heard that before. Well, typically what that would mean is someone who has had some sort of knee surgery of some sort or has inflammation in some joints, when the atmospheric pressure drops, that has an effect on their body and it starts to hurt, said, yep, I think there's a storm coming, because they can tell from that type of inflammation, whether it's a hip, a knee, an ankle, perhaps, just say, yep, pressure's dropping, I can tell, I can feel it. So maybe they should be weather forecasters instead. I never would have believed that we're going to have a late start this morning. I just didn't think that was in the forecast. One thing we can go when saying, well, at least it's a late start and not a cancellation of school. Because I think everyone would agree that when the semester starts, yeah, we might get a day off here or there and think that's okay, but we're already up to 6. And how many of you are thinking that's enough? 1, 2, 3. Just 3 of you? 4 of you? Okay. You want more off? Yesterday was just so stressful. Okay, fair enough. Everyone has their own reasons. All right. So what this means is the standard unit for pressure is an atmosphere. So if you want to, typically you can put 1 in front, that's fine. So an atmosphere of pressure equals 760 millimeters of mercury. Now that doesn't mean anything to you right now, but we'll make some distinctions or examples of how that was used as a measurement at one time. Or 1 atmosphere can also equal 101.325 kilopascals. And it doesn't really matter if you write it like that. Typically, I just put the K is lowercase and the P is capitalized and the lowercase a. And it's really not that serious whether, oh geez, I gotta have them all capitalized or all lowercase, just so we know what it is that you're referring to when we're talking about kilopascals. Okay, and we're not too concerned about square inches or pounds per square inch, but some of you that does pertain to, of course, your vehicle. Where does PSI utilize in your vehicles? On your tires. Okay. How many of you think, just looking at it, yeah, it's good? Or do you just wait till the tire light comes on to say, yep, I need to add air? Okay. And I would probably I'm probably just as guilty unless the sensor comes on. There's maybe nothing to really worry about, but checking it every now and then is a good idea. And sometimes you can just rely on, well, if you're having your vehicle maintenance for possibly changing the oil, well then typically it gets done there because they're probably rotating the tires and whatnot, which is a good idea to have done as well. But anyway, probably a good rule of thumb is probably somewhere around 35 to, I suppose, I don't think you really want to get too much over 40 PSI in your tires. Because once you start to overinflate them, what happens is you're not making very good contact on the road. Rather than having nice contact like this, I suppose you could say it just starts to push itself out and it bevels like this. And eventually I think you could blow out a tire. You could also blow it out if it's too small where it starts to make an indentation like this. And that's probably, in my mind, even worse having too low a pressure as opposed to too much. Neither one of them is very good, but having too low is probably slightly better than, too much is probably slightly better than too low. Anyway, on page 365, okay, one of the things that has some sample problems on there, and what we see happening on is you can go through and you can read the sample problem on your own, but the practice problems on page 365, what it's asking is convert a pressure of 1.75 atmospheres to kilopascals and to millimeters of mercury. So here again, one of the things that we could say, well, you should get 0.98 and make sure, I'm looking at the wrong place. 177 kilopascals and 1330 millimeters of mercury. Knock it out. Right? No. I just told you the answer. I just showed you. There's your conversions right there. Yeah, yes, yes, yes. Come on, I'm popular now. I'm the one banging the. I thought you said thinking of banging that stove drawer. Oh, bang, dang, 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 dang. One thing I'm missing is the sun. Oh, wait, wait, wait. Oh, yeah, there it is. There it is. And I think they're even gray. Yeah, now we're looking pretty popular now. Just like that, right? Oh, yeah, the only thing I'm missing is the stove. Yep. I don't think so, Jill. Okay. And a holler. Yeah, no. Okay, so convert the pressure of 1.75 atmospheres, okay? So this is still dimensional analysis, 1.75 atmospheres. So we want millimeters of mercury in kilopascals. So someone what do you want to change to first? Which one of those? Okay, so we said for kilopascals we want to have 177. Well, this is what 1 atmosphere equals. So, in order to get atmospheres to cancel in our second step, just like when we're canceling moles or canceling grams, where would we put atmospheres in our second step? On the bottom. So for every atmosphere then, how many kilopascals is that? Okay? So these you're probably going to memorize just because you're using them over and over again. Okay, so once we go about doing that and we take 1.75 times 101.325, surprise, surprise, 177. Just like what we had predicted, 177 kilopascals. Okay, 177 kPa. All right. Then, as we proceed further along, we want to do millimeters of mercury now. Okay, so what that means is we've got how many? We're still taking, yes, 1.75 atmospheres. 1.75 atmospheres, and converting that to millimeters of mercury. So in this step, instead, how many millimeters of mercury are in an atmosphere? 760. 760 mmHg to an atmosphere. Okay? Therefore, we said they're supposed to get about 1330. Well, probably no surprise, we take 1.75 times 760 and we get 1330. Okay. And millimeters of mercury. Okay. Now, one of the aspects that we start studying right away when we're talking about pressures of gases is what we call manometers. Okay, and those are used in many different applications. We could say is even for instance, jet planes would have a manometer on there because it measures the pressure differential on where maybe that plane is in the atmosphere, and what a computer would analyze with that airflow going into what's called a pitot tube. It measures the pressure differential and then also ties into that of the airspeed of that plane as well. So there's lots of applications that pressures of gases are used for, way beyond that of just forecasting weather than what you'd ever think of. There's really no reason that you would have ever thought of that unless someone had told you. But how are you going to know unless someone shows you or tells you? Yeah, you wouldn't. But when it comes to problem solving for these, when it comes to a manometer, Okay? Now, whether you would have to do something like this in college, I'm really not sure. Maybe that's not even used anymore. They might not even talk about it. But if we back up one page, okay, we're talking about J tubes, okay? And one of the things that we see in figure 3, okay, is talking about torselli. And a torr, or T-O-R-R, is also a way of measuring that of gases as well. In that figure 3, goes on to talk about Torricelli discovered that pressure of the atmosphere supports a column of mercury about 760 millimeters above the surface of the mercury in a dish. Now, how many millimeters are in a meter then? Because when we think of that of a, okay, so sometimes I got to think about that too. If we have a meter here, okay, then of course we have what's called a decimeter, then here's our centimeter, and then here's our millimeter, millimeter way out here. So if we have a meter here, this is 10, this is 100, then here's 1,000, okay? So what we see happening then, 760 millimeters of mercury is about 3/4 of the way up on that meter stick, okay? As we're just increasing those in powers of 10. So I don't know, something, if this is maybe about a meter, well then 760 is probably somewhere about right in there. Yes. Okay? And this is just so you kind of have an idea of what 760 would actually look like. And that's what they're illustrating here in maybe figure 3. But anyway, in figure 4, just below it, okay, in a manometer, one of the aspects we were just talking about, above, the pressure of the oxygen gas in a flask pushes on the mercury column. Okay, so when that happens, the difference in the height of the mercury in the two arms of the U-tube indicates the oxygen gas pressure. But one of the things that we talk about is not only just a closed manometer, that's what you're looking at there. We talk about open manometers as well. And sometimes with, well, I shouldn't say sometimes, with those you have to do what's called a correction because it's open to the atmosphere. What they show here, what is on the very top of that J tube in figure 4 that you look at, it's pointing to it and it starts with a V. It's got a vacuum in there. So what that means is that tube was sealed off to the atmosphere. When you do problems like that, those are much easier because you don't have to do that correction because it's not open to the atmosphere. The tube was sealed with vacuum pressure, and then again, those are much easier to solve because you don't do this pressure correction like I'm going to show you. So please bear with me. Some of my drawings aren't the best, and I get that. And I wonder if they show a picture of an open manometer. I was thinking that they did. Somewhere here in one of their special inserts in the chapter. No, I'm not seeing it yet. But I suppose that example that we had observed on, what was that, 363 is about as close as we're going to get. But that's okay. So you know what a J tube looks like because that kind of resembles a J. So what that means is, for instance, I'll try to keep this from being too word-y or having too many words in it, is, for instance, what is the atmospheric pressure in an open manometer. If the mercury is, we'll say, 42 millimeters higher in the, we'll say, atmospheric arm. Okay, so I guess that's a question. Okay, so one of the aspects that we want this to be in is in millimeters, because that's where you're going to have to do some of these conversions in, because one of the things that we're talking about is the pressure of a gas, we'll just say O2. Now, what you're reading this thing, and this doesn't make any sense, but that's why we'll draw a diagram to hopefully connect the dots here, okay? Of O2 flask is, we're going to say, we'll say 94 kPa. Okay? So what this means is we need to convert that 94 kilopascals into millimeters of mercury then. Okay? Or excuse me, this 42 millimeters of mercury into kilopascals. And this is why. Because when we're looking at this container, we said we're going to try to connect the dots here. It would be very similar to what you're looking at there on page 363 in figure 4. If we have this flask here, okay, got this big tube here, and it's called a J tube. Okay, do we have a visitor in here? Oh, okay. The thief. No, he's not a thief. At least he brought it back for you. Okay. So here we got this oxygen gas in here that we're referring to in this question. It says the pressure of O2 in the flask is 94 kilopascals. Okay. So what we see happening then is we got this fluid in here, because as you're looking at this J tube, that gray solution in there, that is mercury inside that column. Okay, so what we see happening here is, for instance, this is one where the mercury is starting to either seep into heat, well, not seep into it, but start to move up and down in this column, and then here's the other end of it. And this is mercury inside of this J tube here. And what we see happening is there's 42 increments in between the two. In other words, this line here and then this line here, there is a distance of 42 millimeters there. Okay? And one of the aspects that you're going to want to know, because there's an extra correction that you have to do, because this is open to the atmosphere. How is this different than what you see on page 363? That's closed and in a vacuum. But if this is open, there's just one extra step that you have to take. And the way to look at that is, I like to look at, we got this dotted line here. And this dotted line is separating our two arms, because we have one that's called an atmospheric arm, okay, and another one that's called a gas sample arm. So, according to this picture, along that dotted line, which side would you believe is the atmospheric arm? The one on the right or the one on the left? So which one would be the atmospheric arm? The one on the right of that dotted line or the one on the left? Which one is open to the atmosphere? The right one, because this isn't a closed manometer, because that figure is showing a vacuum seal up here, but it's not vacuum seal, it's open to the atmosphere then. I guess probably should have this sealed off. Say there's a gas seal, or not a gas seal, but a valve on there that doesn't let that gas escape. But this is how some of the early manometers would actually work. You'd have that open to the atmosphere, and as that atmospheric pressure changes, that changes that amount of mercury inside that column. Sometimes it's higher in the gas sample arm, sometimes it's higher in the atmospheric arm. So one way to distinguish that, this side is the gas sample of this dotted line, and then the right side is the atmospheric arm. So I'll just put A there. Okay. Now, one of the things we have to do is account for this 42. This 42 millimeters of mercury we need to convert to kilopascals. Yes? Yes. So one of the things that we would do, this is going to be a three-step problem, because notice we went from atmospheres to kilopascals, or we went from atmospheres to millimeters of mercury. We did not go from millimeters of mercury to kilopascals. That's not a two-step problem, that's a three-step, and this is why. Okay? We can't go straight from millimeters of mercury into kilopascals without going through this first, because this is the only one that is equal to both of them. These aren't equal to one another unless you go through the atmospheres first. So, what we would do is we're going to take this 42 millimeters, and you don't have to put mmHg every time. We know that we're talking about mercury every time. So 42 millimeters. How many of those millimeters are equal to an atmosphere? Okay, so once we've done this, for every 760 millimeters of mercury, we get an atmosphere. Okay, so now it's just one way of looking at it is you're going this way, over, and down, because there is no conversion between millimeters and kilopascals unless you go through the atmospheres first. Okay, well, I suppose there is if you just went to Google, or what do? You may go home and say, Alexa, if we have 42 millimeters of mercury, how many kilopascals is that? And then it spits it out for, I don't know if it does. Yes?
It's kind of like atoms, moles, grams.
Exactly. Well, the dimensional analysis problem solving is exactly like that. But I think we'd all agree that it's just the variables that are different. Now, how many of you are looking at this and scratching your head and saying, oh my gosh, this is terrible? But we've only spent, what, 20 minutes on this. So we really don't know how good or how bad this could be. Okay, so we are now in atmospheres. So we've made our way from here, okay? Now we can get into kilopascals by making this correction. So these are gone, okay? Now, how do we get rid of that atmosphere? Because we don't want atmospheres, we want kilopascals. Okay, so for every atmosphere now, how many kilopascals do we get? kPa. Okay, so now these are gone. We're in kPa, which is what we want because we got to do this correction factor here. Okay, so upon doing that, taking 42 times 101.325, that gives us a large number, 4,255, but after multiplying these, what do we have to do yet? We need to divide that number by 760, That gives us an answer of 5.59, which we will say 5.60. Okay, so that equals 5.60. Almost did it again. Kilopascals. Almost wrote millimeters of mercury. So kilopascals. Now we've got two numbers with the same label on there. But remember, we had said that we liked closed manometers a lot better because you don't have to do this final correction factor, because this open manometer is just as open to the atmosphere. So we would be done. Yep. So what we see happening then is another aspect. Since this is atmospheric arm, just picture always add. Okay? So if this mercury is higher in the atmospheric arm, or AA, we're going to say always add. So since it is higher on this side, which it is, we're going to take this 5.60 and do what in reference to 94? Add it, because that's why we want to label that as always add an atmospheric arm. So that gives us 99.6. That looks correct, which I do believe it is. So then your correction factor then, because of this open manometer, we're taking this 5.60 and we add that because it's higher in the atmospheric arm, 99.60 kilopascals. Okay. And I got to double check this too, but what would happen is if this was a closed manometer, like you would say, if it's 42 millimeters higher in, doesn't matter, either arm, and it wouldn't say the pressure is 94 kPa, you just make this conversion, okay, into kilopascals, then you're done. You don't have to take that extra step. Again, the only reason we're doing that is because this was open to the atmosphere. It's the only reason. Okay? And if nothing else, I think this helps reinforce problem solving, which is always going to be a aspect of being successful taking college classes, and knowing how to problem solve, or how to go about getting off the moon when we're there by ourselves. But you got your sugar supply. Okay? Anyway, we will pick up with this a little more tomorrow and start talking about Boyle's and Charles's gas laws.